All right, I hit the record button, and so now this is recording. This is the written homework for week 4. This is our review session for tonight. We're going to be going over 4 problems. A lot of these are going to involve friction or identifying, once again, just kind of like a review of, not last week, but the week before, of Newton's laws, how to set up F-net equations and how to determine forces from them once you set them up. So hopefully it goes pretty quick. I can see like the last couple of problems, like after we finish with problem 1, I think it's going to be relatively smooth sailing, hopefully. So yeah, let's go ahead and get started here. So for problem 1, we have pushing a book. So it says you hold the book stationary by pushing it directly against the wall. The book's mass is 1.5 kilograms, and you push at it with a force of magnitude 200 newtons, pointing in the positive x direction. In the usual coordinates, it says to ignore friction between your hand and the book, but not between the book and the wall. So that's a very interesting little bit right here where it says ignore friction between your hand and the book, but not between the book and the wall, right? So that means like this little area here, there might be friction between your hand and the book, but we're going to ignore that, and then we have to account for the friction that's in between the book and the wall for sure. So before we get started on any problem, we have to always kind of look at what information is given to us and kind of label that out, right? So we have mass is 1.5 kilograms, and we have a push force, right? F push with a magnitude of 200 newtons, right? So that's the information that's given to us, and we can't ignore the friction between the book and the wall. So that being said, we can move on to part A. So it says draw a free body diagram of the book. Keep in mind that normal forces are perpendicular to the surface of contact, and that's something I repeated a lot in previous sessions as well. So yeah, keep the force is perpendicular to the surface of contact between two objects, and that the friction force is parallel to the surface of contact. To determine the direction of the friction force, think about the direction in which the book would slip if there was no friction between the book and the wall. So they actually did a lot of the work there for understanding the directions of all this for you guys. So for our year, they just told us to figure out the forces. So they had parts A, B, C, and D to figure out the forces, but yeah, they, if anything, just want us to figure out the free body diagram on our own without looking at or trying to interpret anything. So if we're trying to figure out the free body diagram, we'll draw like a little dot here to represent the book, right? So anyone want to guess what kind of forces we have acting, other than maybe the stated obvious ones on the book? So yeah, for sure we have gravity, right? So that's usually going to be, well, not usually, always going to be pointing down. So that's gravity there, right? So that's on the book. Anything else? Normal force? Yep, absolutely. So we're going to have a normal force, and that's going to be pointing perpendicular to the surface of contact, right? Because the surface of contact is the wall here. So perpendicular would mean making a right angle with, right? So there's normal, right? What else? What other forces do we have acting on the book? So there's F push, right? Excellent. So there's F push. Oops, there. I want to actually make it proportional to the normal force. So anyone know also why I need to make it proportional? Like, why do I need to draw Fn equal to F push in terms of the length, right? Because it's not moving in the x direction, right? It's not going through the wall, and it's not, just, I guess, moving to the left, right? It's not levitating or anything, so there's no movement across the x-axis at all, right? And now the same thing for the y-axis too, because obviously, like in the context of the problem overall, there's completely no movement. But someone also stated that there is static friction, right? So there's absolutely static friction because we have the friction force. They determined that the direction it would be pointing would be, so it says determine the direction of the friction force. Think about the direction in which the book would slip if there was no friction between the book and the wall. So the book would slip what? what direction would the book slip in? If we just removed our hand, right, where would it go? Down, right, because of gravity. The book would just slip downwards. So in order to counteract that intended motion, or that normal motion of the book, static friction would have to be pointing in the opposite direction. So it'd have to point upwards like that, Fs prime, and then that would have to be also proportional to the length of Fg, because once again, book is held stationary, so we don't want any forces, net forces in the x direction, and no net forces in the y direction. So that is our free body diagram. They didn't state to put any superscripts, so usually I would just ignore that, but just for the sake of explaining what's going on here, I'll kind of just really briefly kind of go over them. So for gravity, you obviously have the force of gravity of the earth acting on the book, so that would be like earth on book, right? Your F push would be hand on book, if they were to ask you what the superscripts are. Your normal force, right, that would be wall on book, basically. And then static friction, that would just be like the wall on book as well. So those would be your superscripts if they were to ask you for them, but I don't think they are indicating that you need to use them. So this would be your free body diagram for part A. Yeah, I can explain again why static friction force is upward. So they said here, they determine the direction of the friction force, the direction in which the book would slip if there was no friction. So the book would naturally slip if we removed our hand, it would go downwards, right, due to gravity, because gravity would then be the net force, because you don't have anything in the x. Net force would bring it down, because in that case, the book would kind of be in free fall, right? It would be brought down by gravity. So in order to oppose that force, by gravity, there has to be that static friction force pointing upward to cancel out any motion in the y direction. Does that make sense? Yeah, so just basically they keep net force 0, right? Because otherwise, if you didn't have a static friction force, there would be some slippage, right? Because there would be a net y force pulling it down, basically. Make sense? Yep, no problem. Any other questions about part A with regards to the free body diagram? Yeah, go ahead. Oh, wow. Okay, so this looks like, that's not good. Okay, so I'm guessing then that some of you guys have professors who aren't all on the same page with the other professors, I guess. So, do you know who your, what a stupid question. Okay, who's your professor? Not do you know who your professor is? Who's your professor? Okay, yeah, okay, I got you. Okay. So, this is, yeah, okay, shoot. Um, wow, okay, how do I manage this? Because this one I grabbed straight off of Dr. De Jong's Blackboard page, which is usually my go-to, but I was not aware that they actually had different, um, like, parts and stuff. So, quick question then. Does problem 3, real quick, look different? Because, yeah, go ahead, sorry. Okay, so in that case, then 2 out of 3 professors do actually have the written homework from my year. So yeah, they reused the written homework that I had when I took 131, and I personally believe this one is a little bit more difficult. Um, okay, so that's not a problem. Okay, so I guess I'll just kind of do like double the work basically. I'll make sure to upload my um, stuff for the old written homework, the one that you guys have for Dr. Ansari and Dr. Yordanova. So I'll upload that on the Google Drive so you guys have access to that as well, because it's going to be a little bit difficult to kind of manage in between the two. But for problem 1, I'm guessing that you guys had, for part A, it says, what direction does the normal force from the wall on the book point? And explain how you can tell. So that's what it says for part A on the other document. So, direction normal force from the wall on the book, that would be pointing naturally in the negative x direction, right? Because normal force here is the perpendicular contact force, right? So it's the force that is perpendicular to the contact surface. So if this is the contact surface here, right? Normal force will be pointing to the left in order to kind of give solidity to the wall, right? It's the force that's going to be pushing against the object that it's in contact with, right? To make sure that that object is not going through the wall or anything like that, right? So it gives solidity basically to this wall. So normal force is pointing in the negative x direction. It points perpendicular, right? It points in the direction perpendicular to the surface, so it makes a right angle with the surface. And it points in a direction that'll keep the book from passing through the surface. So that normally if we were to push, if there wasn't any surface here, if we push this way, the book would continue going to the right. Because there's a surface here, right, and we want the normal force is going to be the force that is perpendicular to that contact surface and is going to be keeping the book from passing through the wall. So negative x direction, and then for the explanation for the reasons I kind of explained there. And then for part B on Yordanova and Dr. Ansari's worksheet, I believe part B says, what direction does the frictional force from the wall on the book point? So they really just kind of, I guess, broke up part A into little bits and pieces. So they just made it A, B, just because we already kind of explained part B as well, right? For the frictional force, for it to be pointing upwards in the positive y direction, right? That's because it needs to oppose that force of gravity, right? So the frictional force acts opposite or against the intended motion if the book were let go, right? So if the book were let go, it would be moving downwards. And so the frictional force has to cancel that downward motion, that force of gravity, in order to keep the book stationary, right? So, so book is not moving in the vertical direction nor in the x direction based on the context of the problem, because the book is being held stationary. So since gravity is pointing downwards, frictional force would have to be pointing upwards in order to counteract the effects of gravity. And at the same time, I guess you can also add that it would not be pointing in an x direction because we already have these forces canceled out, right? So you can also add that factor into your explanation. So you can say that we already have a push force to the right and a normal force that is equal but opposite so equal in magnitude, opposite in direction to that push force. So that gives us a net force of 0 in the x direction. So the only thing that would be left that would be giving a net force would be this gravity force in the y direction. So in order to cancel this out, static frictional force would have to be pointing upwards. Does that make sense overall? For those who are in Ansari's and Yordanova's section. Oh, Ansari's is the same as De Jong. Okay, my bad. I thought both of them were different. Okay, so in that case, okay, I'll just stop referring to Ansari's then. But yeah, for those who are in Yordanova's section, are we good there for the explanations for parts A and B? Yes? Okay, cool. Part B then, we move on to part B. It says, what is the magnitude of the normal force from the wall on the block? Or on the book, sorry. So we want to find out this normal force here, right? So this is kind of like an action-reaction pair in a sense, right? Because this normal force is wall on book, and the push force is book on wall, essentially, or hand on book, but I guess it'd be the book pushing against the wall, essentially, right? Because the wall is feeling the pressure from the book, the wall exerts a force kind of back on that, right? So we can kind of think about it that way. So if we want to figure out what the normal force is, right, we have access to this F push force, right? We know that F push is equal to 200 newtons, right? So if there's no movement in the x direction, based on the context of the problem, because the book is stationary, and based on our free body diagram, what can we do to figure out the normal force here? Do you use an equation or what? Yeah, so set them equal to 0 because they're at rest. And then more specifically, we're going to set up an F net equation, right? So F net x, right, is equal to the F push force, and that's pointing to the right. And then we can say minus the normal force, right? And that's equal to 0 newtons, right? Because the net force would be 0 because it's not moving in the x direction at all. There's no net force in the x direction. So in that case, F push would just be equal to Fn, right? And so F push is equal to Fn. Fn would then equal 200 newtons, right? So Fn is 200 newtons there. So kind of referring back to my previous videos, I integrated direction here when I put in the negative sign, right? So I indicated that this negative sign right here indicates that the normal force is pointing in the negative x direction. You could have alternatively put F push plus Fn, and then if you subtract Fn over, right? Or if you, for example, let's say you subtracted F push over, then F push would be equal to, or Fn, sorry, would be equal to negative 200 newtons, which makes sense because this would be pointing in the negative x direction. So if we were just asking what the force is, this would technically be negative 200 newtons or 200 newtons to the left. However, because they're asking for magnitude, and magnitude indicates absolute value, if you were to do that, if you were to do F push plus Fn and solved for it, and you got Fn is equal to negative 200 newtons, right? All you'd have to do is just take the absolute value at the end to figure out the magnitude. I put the negative sign from the begin with in order to indicate the direction, and then all I'm putting in for my force values is just the magnitudes, and that's why I get the magnitude at the end. That's kind of built in right there, so it just makes things easier if you indicate the direction from the beginning. So someone has a question. They're asking, why is F push on our free body diagram, if it's not a force on the book, F push is the force from the book on the wall. So it's a push force from your hand on the book, but it's also like, I mean, yes, the hand is pushing on the book, but at the same time, like, is the book not pushing against that wall, basically? That's kind of the approach that we're kind of going for here. So, like, if we were to say, yeah, F push, it would be, hand on book, technically, right? But if we're looking at, like, what's going on between the book and the wall, right? And that's mostly what we're going for, because we put static friction force being, or acting, right? So the wall is acting on the book, normal force is the book, or the wall acting on the book as well. So it's all kind of in the context of the book and the wall, wall and the book, right? But technically, from the begin with, right? If we're just looking at what forces what is the agent of the force, the push force, that would be the hand on the book, right? But essentially, if we're just looking at like what's acting on the wall and what is acting on the book, well, there's a force of 200 newtons kind of pushing on that book, and that force is kind of transferred to the wall, and then the wall pushes back with that same force but in an opposite direction, if that makes sense. Sound good? Yep, no worries. Any other questions for part C? Going once, going twice. Okay, I guess no one wants to bid for, or not for part B, part B, my bad, not part C. Yeah, so I guess maybe that was confusing, sorry. So I'm guessing everyone's okay with part B. That sounds good. Then we'll move on to part C. Part C, I think, part B is the part C for Jordanova section. So part B corresponds to part C on the written homework for Jordanova section. So part C now should correspond to part D on Jordanova section as well, just for those who are going to be watching this back online or joining later or whatever. So part C now is asking what is the magnitude of the friction force from the wall on the book, right? So we want to figure out static friction force, wall on book, right? So if we are asking about the friction force, right, what direction are we looking at here? Y direction, right? Excellent. So static friction force, we kind of determined that already to be in the positive Y direction. So what other forces are in question? Just the gravity force, right? Force of gravity. And that's Earth on book, right? So this is kind of similar to part B, where we have to figure out this force. We can also technically figure out gravity, right? Because we have access to the mass, right? And we know that gravity is equal to mg. Force of gravity is equal to mg, so we have 1.5 kilograms times 10 meters per second squared, and that gives us 15 newtons, and that's the magnitude of our gravity force. Now, if we were to just ask for, like, what is the force of gravity, right? Technically, we would have to add that little negative sign there to indicate that this is negative 15 newtons, or 15 newtons in the negative y direction. But since we're kind of dealing with magnitudes, and then the way that I'm going to be setting up my equation, I'm going to be integrating direction already with the signs and stuff. I'm just going to be plugging in magnitudes. So for my F net y, what does that look like? Anyone want to take a shot? Yes, it is equal to 0. There's no doubt about that. I was actually asking kind of more about like how the forces would be set up. Yeah, there we go. So Fs minus Fg. But yeah, absolutely right. It's equal to 0. So yeah, friction force minus the gravity force, right? So in that case, Fs would just be equal to Fg, right? And so Fs would just be equal to 15 newtons at that point. And that's the magnitude of the friction force. And so regardless of magnitude or not, since the static friction force is also pointing in the upwards positive y direction, this also happens to be just the natural like direction too for the static friction force. Now, if you were to choose to say, okay, Fs prime plus Fg, right, is equal to 0, well, that's when you would have to add this negative sign here, because then you have to indicate the direction for the gravity force. So this would be Fs plus a negative 15 newtons, and then that's equal to 0. And then you add the negative 15 over here, and that becomes positive 15, and that's where you get 15 newtons equal to Fs. Like I said, I highly recommend integrating the direction at the start of your problem, as opposed to going back and kind of putting in negative signs, because that'll just mess you up. But either way, you can see I like to explain both ways just so people have options. And yeah, mg is equals to mass times gravity. Yeah, mg is mass times gravity. So mass times the acceleration due to gravity, 1.5 kilograms times 10 meters per second squared. Sound good for problem 1? Any questions at all? Nope. Okay. I'm going to move on to problem 2. Problem 2 is also different to Jordanova section. I believe part A is fine. The distinction between this one and the one that Jordanova section has is that Jordanova section gives you the tension force. They give you what the tension force is, but they don't give you the mass. And then for this problem, for De Jong and Ansari, they give you the mass, and you're eventually going to have to find out the tension force, right? And more specifically, the components of the tension force as well. So, it says, a fish is suspended by a string held by a fastener at point B. This is animal cruelty. This fastener is attached to two other strings, A and C. The mass of the fish is 0.6 kilograms. You may assume the strings are all massless. Okay, awesome. So once again, we can't jump to we can't jump to conclusions, right? We can just go to part A. You have to put out or label what we have access to. We have access to mass is equal to 0.6 kilograms, right? The strings are all massless, so there's no mass contributed by the strings. And the fish is suspended, right? So it's being tortured, I guess. So part A, it says consider the fish, the string it's hanging from, and the fastener as a single object, right? So this whole deal here is a single object. Draw and label a free body diagram for this object. So so if we're considering this whole thing to be one object, right, you have to watch out for something. So imagine like this whole part here is our dot that we put for the free body diagram. This whole thing is our dot, right? Now, a mistake that you can easily make is that, okay, well, here's a rope, right? Here's a string here. So wouldn't there be a tension force here? Well, no, because once again, they want us to consider the fish, the string, and the fastener as one single object. So this is like, if we like drew a big circle, this is what would it be? So in that case, this little dot here is the fastener, the string, and the fish, right? And we know that the fastener and the string and stuff, they're massless components. So really, what forces, well, yeah, I'll just ask, what forces do we have acting on the fish here? So gravity, yes. You have force of gravity, and that's due to the fish, right? Fish is pulling it down. We have tension, right? So where do we have tension exactly? So yeah, excellent. So we have tension in the negative x due to the string A to B here, right? So we have this way. And where else do we have tension? Now remember, we said we can't have tension here because this was part of the object anyway. And so yeah, we have tension going northeast, right? Or that B to C section right there. So we have, this is, I'll just call this C, and this I'll call this A, right? So that's our free body diagram. We've contributed all the forces. I believe someone said normal force here earlier, but I don't know if that was a mistake or not. But the normal force would not be a factor here because there technically isn't a contact surface, right? We don't have like this fish isn't like on a wall or on a, in contact with the floor, or isn't, pushed up against a wall or anything, right? It's had enough being hanged by a little string, so there's no contact surface that we would have here that would contribute a normal force. So yeah, normal force isn't part of any of our equations there, but hopefully that makes sense for part A. Part B, okay, we have a question here. So if the object is at rest, then the net force is always 0. Yeah, pretty much if you have an object at rest, net force is going to be 0. The problem is just figuring out like the components that are contributing in each direction to a net force of 0, right? Because you have A and C, those are going to be your tension forces, right? A is solely in the x direction. C has both an x and a y component, right? And gravity is solely in the y direction. So you kind of have to like then go on to figure out how the components factor in to make that net force 0. But yeah, since this is at rest, F net is 0. For part B, it says find the magnitude of the tension force in string C. So, oops. It says you may approach this in 2 steps. First, use Newton's second law in the vertical y direction to compute the y component of the tension in that string. Next, since you know the angle at which the tension force is exerted and know its y component, you can compute the magnitude of the tension force. So what this means is that, okay, if we have string C, right, this string C right here, there's an x and a y component to it, right? If I want to figure out the magnitude of this is, I can do it in two ways, I believe. I can either do, well, I actually no, I take that back. You can't do that quite yet, but you would have to look at what you have and what you don't have, right? So this force of gravity, we can figure this out, right? So we have this force of gravity, and yeah, absolutely, we have to get the opposites of the forces. So we can't find out A yet, because the opposite of A would be that Cx, right? So there's a little x component of the tension force here. But we don't know what C is, nor do we know Cy, so we can't figure out Cx yet. And obviously from there, we can't figure out A, because that's obviously what we're doing for part C as well. But we do have access to some information that can give us stuff in the y direction, right? So that's always kind of the mentality that you guys have to go about when solving these problems, is like, okay, what do I have access to? What do I need to figure out? And then from there, like, what information can I calculate? What things can I extract from the problem to help me figure out the unknown? So in that case, we have the mass of the fish is 0.6 kilograms, right? From that, we can figure out the force of gravity right then and there. So force of gravity is mg, and that's 0.6 kilograms times 10 meters per second squared, right? And that's just 6 newtons there, right? 6 newtons for the force of gravity, and that's the magnitude of the force of gravity. Keep that in mind. So we have this force right here, and then based on the context of the problem too, we know that this fish is being held or suspended stationary, right? If there's no movement at all, nor in the y-x direction or the x direction, right? So in that case, we have this Fg, and then we also have this Cy component, right? This Cy component for the tension force of C. So what can we do to figure out this C force here? This is kind of extrapolating, because if we have access to Fg, we can easily figure out Cy, right? Because if we can set up like an F net y equation, right, we can say that, okay, the F net, the net force of the whole thing is 0, right? There's no motion in the y direction whatsoever. So that is equal to 0, and we have access to this. We can figure out Cy, right? But from this Cy, how can we figure out C? What can we do? This is kind of like far into the problem, but I just want to figure out if you guys have an understanding of what the next step is. Yep, excellent. We're going to do some trig. So you can use trigonometric functions, and we have this angle here that's 30 degrees, and from that value of Cy and this angle, right, we can figure out the magnitude of C. So first of all, though, step by step, we have to figure out what the F net y is. So we know that the net force is 0, because there's no motion in the y direction. But what is the equation? How do we set it up? Yeah, not C minus A, not quite. Because then C minus A would be like doing these, right? And so we're trying to figure out what's in the y direction solely. You can go, I mean, like, I'm just doing this step by step. Yeah, Cy is like, if we do the problem, Cy is absolutely 6 newtons. Yeah, no, I'm just trying to like go step by step just to make sure that everyone sees what's going on. No, you're not overthinking. Like, you're like quickly thinking, I guess. Like, you're super thinking. So good on you for understanding like what's going on. You're able to figure that out real quick. But Cy, right, is in that positive y direction. And so I'm just, yeah, so Ramses, like, I'm just going in the y direction only. This would be in the x direction, so I don't want to factor that in quite yet. So it would be Cy minus Fg, right? And this, Cy minus 6 newtons that we figured out here. And so yeah, Cy is going to be equal to 6 newtons as well. So So you're fine. That's absolutely right. And if you don't want to go through the whole equation thing, which, I mean, actually I can't even like recommend not doing the equation because they will count you points off if you don't have like your work shown. So I definitely 100% always recommend writing out the equation. CY is the same as FTY. It's just that you have two strings here. So you would kind of say like this is like FTYC, and this would be like, well, this is just like FTXA or something, right? So the reason why we're not saying like FT, like force of tension as usual, is because of like the fact that we have two strings here. So it's going to be really different to get the notation down. It'll just be really icky because we would have to like indicate like, okay, this is force of tension of C in the Y direction. It would kind of look like that, which is just really ugly. So yeah, I think it's just, personally, I think it's just a lot easier if you just go ahead and indicate that this is like CY, this is CX, this is like AX or something. Label that in the problem, and the TAs or the professors, whoever's grading, is going to understand what's going on. It's just that the whole FTCY, FTCX is just really, there's just a bunch of terms there jumbled. But that's the Y component of the tension force in string C. So if we want to figure out what the magnitude of the overall string C is, right, we can use trig again. So if this is 6 newtons, this is C. Well, that looks more like an O. This is C, right? We have this 30-degree angle there, right? What trigonometric function can we use to figure out the overall magnitude of the tension force in string C? So we have this angle, we have this side, and we want to figure out this. Would we use tangent? Because tangent, remember, is opposite over adjacent, right? So if we did like tangent of 30, that would give us CY over CX, and we have CY. So this could, tangent could technically give us CX, right? But we would be using sine, right? Because sine is opposite over hypotenuse, right? Sine is opposite over hypotenuse. So sine of 30 would be equal to CY over C, right? So it's the side that is opposite the angle, divided by the side that is the hypotenuse, the longest side of a triangle, right? So opposite over hypotenuse. So 6 newtons over C is equal to sine 30. So sine 30 is equal to, 6 newtons over C, right? And so then you'd have C sine 30 is equal to 6 newtons, and then C is equal to 6 over sine 30. I don't have my calculator on me. For some stupid reason, I never bring my calculator to these sessions. I think usually the math isn't bad, but for some reason I just forget to bring the calculator. But sine 30 is like, what is that, 1/2? No, I can't remember. I should remember the amount of times I did this in calculus, but it wouldn't be 6 sine 30. It would be 6 divided by sine 30, I believe, because if you're doing sine 30 and that's equal to CY over C, it'd be 6 newtons over C, and so you'd have to multiply C over and then divide by that sine 30. So it should be around 12, yeah. So sine 30 is 1/2. Yeah, so 12 newtons there for the tension force for C, right? Sound good? I want to make sure that I did all that correctly. Yep, so we have 0.6 kilograms. We multiply by 10, that's 6 newtons. CY should be 6 newtons, and then, yeah, okay. No worries. But I believe the homework for your de novo section is, once again, slightly different for for part B. I believe they're asking for the maximum mass of the fish that the string A can support before pulling loose. That is going to be a little bit different just because why did we do CY over C? Because it's opposite over hypotenuse. So CY over C is equal to sine 30. Okay, cool. I was like, I sometimes second guess myself, and this is my first time doing the different problems, because I was used to the ones from Jordanova section, and so like I'm doing these live with you guys, so I just want to make sure that like I'm getting all this right, because I have no way of checking of what I'm doing, whether it's right or not. So hopefully like it all makes sense. Please let me know if you guys think anything is off, and I'll like look back at it again. But I'm fairly confident this looks good and it makes sense. It's really difficult for me to kind of like move back and forth between the Jordanova's homework and the homework that you guys have here for De Jong. I guess what I'll do is I'll upload the different questions on Google Drive and have attached, like, I won't attach the answers necessarily, just because obviously we're not giving answers out just for the heck of it. And since I'm not going to be going over it, right, and explaining and stuff, I'll just write kind of like the setup, and I'll upload that. And if you guys have any questions, let me know, and I'll try to answer them as best as I can, and as soon as I can. So I'll upload the different section for part B for the for this problem. Why do we set sine 30 equal to CY over C? So, okay, you guys are all right. Now I'm like really second guessing myself. So this is string C, right? And so we have CY, and we know that's 6 newtons, unless like I did this part wrong, but I'm hoping this is 6 newtons. So in this case, if we want to figure out C, right, and we have this angle, right, let's say 6 newtons over C, right? We can set that equal to something, right? Something. So in that case, what is this something? We can do sine. We can use the trigonometric function sine, and sine is opposite over hypotenuse, right? So sine 30 is a value I can calculate, right? Sine 30 is a value that I can calculate. Now that's equal to opposite over hypotenuse. So opposite over hypotenuse, right? The angle, or the side opposite the angle, divided by the longest side of a triangle, which is the hypotenuse, right? So that's CY over that C. This is your opposite, and this is your hypotenuse, right? That's your opposite, this is your hypotenuse. So in that case, it'd be 6 newtons divided by C is equal to sine 30, right? And I'd have to multiply this over, where this is C sine 30 is equal to 6 newtons, and then divide by sine 30 on either side. And then you get what C is. And so that's 6 divided by 1/2, and that's just 12. Does that make sense overall? Yeah, no worries at all. Like I know this stuff is kind of a refresher for some people, and for some people it's familiar, and it gets confusing too sometimes. But yeah, that's fine. I just want to make sure that like what I'm doing here makes sense, hopefully. But yeah, with regards to the different problems, the variations between Jordanova's section and the other sections with regard to this homework, I'll upload the differences on Google Drive. Sound good? Yep. Okay. Today for sure. Yep. For sure. Yeah, I always make sure to upload all the videos, everything, the same night, barring any issues with my internet. So, and I always update you guys and let you know when everything is uploaded. So, that being said, I think we can move on to part C then. Part C asks for the magnitude of the tension force in string A. Same deal, right? If we set up an F net Y when we're looking at, if we had access to FG, right? That was the only force we knew anything about, or we could have figured anything about, right? Because we calculated FG. And from a Y force, we had this other Y force, which is CY, and we could figure then out c based on trigonometric functions. So now we have c, we have cy, right? We have access to values that can help us figure out cx, right? This x direction. Because fg is not going to help us figure out something in the x direction because that's just in the y direction, right? So in that case, we would be looking at an fnet equation in the x direction to figure out a and cx here, right? So fnet x, we know that to be 0, right? Because there's no motion in the x direction at all, so there's no net force in the x direction. So fnet x is equal to 0. And then we have cx kind of pulling to the right and a pulling to the left. So this should be cx minus a, right? That makes sense because this is pulling to the right, this is pulling to the left. And we can figure out cx, right? How can we figure out cx? How can we figure out this value right here? Because we know this is 12, right? This is 12 now. And this is 6. This is 12, this is 6. Yeah, you can use cosine or tangent. Alternatively, like, this should be very viable. I don't see why there would be any problem in doing this, but since you have the hypotenuse and you have this leg here, and I mean, it's kind of dangerous, but we're assuming that this is a right triangle. I don't see why you couldn't use, like, Pythagorean theorem. You can do 12 squared equals, well, I'll just write out a squared plus b squared equals c squared. Oops, c squared, right? And so, like, you could say, like, 6 squared plus cx squared equals 12 squared, and then figure that out. But I would stick with the sine and cosine, tangent, all that. So you can do tangent, right? You can do tangent 6 over cx, right? Because this would be opposite over adjacent. Or you could also do cosine, so adjacent over hypotenuse. Either one would work. So there's actually like 3 ways you could figure out cx there. You could either do Pythagorean theorem, or cosine or tangent. But yeah, so I would strongly recommend sticking with a trigonometric function because I just don't like assuming too much in a physics problem, which kind of sounds stupid because if you're able to do trigonometric functions, you have a right triangle, right? But I don't know. I just have a paranoia of assuming too much in a physics problem, so I will stick with the trigonometric functions that I have here. So I figure out cx. I'll do cosine because cosine is a little bit easier. I know that cosine of 30 is equal to the adjacent side over the hypotenuse, right? So that's cx over 12 newtons. So 12 cosine 30 should be equal to cx, right? And so that's 12 times, like, what, root 3 over 2? Which is going to be like some kind of decimal. Please let me know what you guys got, because I'm poor without a calculator right now. All right, we got 10.4 for 12 cosine 30. 10.4. Okay. So it seems there's a mild consensus that it's 10.4. Anybody else get 10.4 or not get 10.4 for 12 cosine 30? You can also do it just to double check too. Let's do, if we were to do tangent, right? Tangent would be 6 over cx. 6 over cx is equal to tangent 30. Oops, tangent 30. And so 6 divided by tangent 30 gives us cx. Someone wants to do 6 divided by tangent 30 as well to check. And then if you guys also want to do 12 squared minus 6 squared, do the Pythagorean theorem and check that as well. We can do that. Let me do the Pythagorean theorem real quick. That'll be 144 minus 36, and that's 108, and then the square root of 108. Yep, 10.4. So I think that's pretty safe to say. So yeah, I should be all ways to do it. Cosine, tangent, and Pythagorean theorem will all end up giving you 10.4 for your CX. It's newtons CX, right? So we have 10.4 newtons minus A, and that's equal to 0. And so we can just add over the A. This will give us our magnitude. A should be 10.4 newtons, right? So we can see here that the final answer gives us the magnitude of the force, right? Because otherwise, technically, if I just asked you what the force is on string, what is the tension force on string A? If I just asked you what that is, not the magnitude, I want the actual value for the force. Negative 10.4, yeah, absolutely right, because we have to indicate the direction there. And so if I'm integrating the signs once again in my equation, I end up with a magnitude always. Otherwise, if I did Cx plus A, then I'd subtract this 10.4 over, and then A would be equal to negative 10.4. That gives me the value of A with the direction, and I'd have to take the absolute value of negative 10.4 in order to get the magnitude. So, yeah, that should be the gist of problem 2 as well. Like I said, I will post the stuff for the differences between this section or this homework and the section or the homework from Jordanova section. So hopefully that helps, and I'll let you guys know when that's uploaded to the Google Drive and stuff. And let me know if you guys have any questions as well about that. I don't know if I could try to have a second session tomorrow, just really briefly going over like the differences in those problems, but I'll see. If anything, I can write up like explanations to the differences in those problems. But yeah. Yeah, if you want to go ahead and do it the normal way, like not the normal way, I guess just the second way, Cx plus A, and then take the magnitude at the end, be my guest. No worries, just be sure that your directions and everything are inputted correctly and properly, and that you're not messing anything up, because you could very well put like Cx plus A and then forget to add in or I guess, yeah, I mean, sometimes like people will forget to put in the directions and stuff, and they'll just leave the magnitude there, and so that messes up the rest of the equation, right? So yeah, just be sure that you're inputting things properly. When do recordings of homework review sessions usually get updated? So within an hour or two maximum, I have the recordings uploaded both on YouTube and on the Google Drive. YouTube is a lot faster. So Google Drive, it'll be uploaded physically faster than YouTube, but it takes like forever to process. And so that's why I do both, because YouTube is just faster at getting like the actual processing done. Google Drive, if you happen to have some fast internet and you're able to download the video, which is like usually around 2-3 gigs, then you can download the video directly to your computer via Google Drive. Or if you don't have fast internet, or if you have caps on the internet or whatever, YouTube is just easier and more user-friendly, where it'll be up and running a lot faster than Google Drive within an hour or two, hopefully. And then documents don't take any time at all, and I'll have those uploaded like within minutes of this session. Hopefully, crossing my fingers. I think I just need to make some edits to the homework and hide the answers and stuff. But yeah, no problem. But yeah, everything sound good for problem 2? I'm gonna assume so there for problem 2. And like I said, I'll indicate the differences between these problems, and I'll upload them for you guys, and I'll write up some explanations for the questions, so hopefully you guys aren't left out there for your Jordanova section. But for problem 3 now, problem 3 is where everything gets bogus. Problem 3 is like, I just, for some reason, it's not like horrible. It's just this concept of like 2 boxes next to each other. Like, that's my worst nightmare for a physics exam or like I can handle everything else. For some reason, like when I ever see two boxes next to each other, it's like it's a nightmare. And so especially too, like man, if you give me two boxes on top of each other, it's over with. Because that happened on an exam, and I think I messed up like the directions of the forces and stuff, or I forgot like to add a force or something. And so you just watch out for these problems. Like I'm like 90% sure one of these bad boys is gonna pop up on the exam. So that being said, I'll go over the problem here and hopefully it kind of makes sense. And for sure, part B right here, absolutely 100%. If it pops up on an exam, like I'm like, there's no way that they don't ask you to draw a free body diagram for both boxes. Like it's absolutely essential that they ask you for that because that's just points that they think that are easy that they want you to rack up. For me, it's not. I guess maybe for you it might be easier. So we'll see. Maybe you'll be better than me at understanding this. Yeah, two boxes is just it freaks me out. I don't like two boxes. Give me one box and I'll figure out the free body diagram. But two boxes is where I start messing up. So hopefully I don't do that because this is my first time seeing this problem as well. But boxes A and B are in contact on a horizontal frictionless surface. So from the begin with, we don't have any friction. We can ignore that. Box A has mass 20 kilograms. So mass A is 20 kilograms. Mass B is 5 kilograms, right? And we have this push force, hand on A, is equal to 250 newtons. That's the magnitude of the force. Both boxes move together with the same velocity and the same acceleration. All right, so, okay, I gotta prepare myself. What is the acceleration of the two box system in meters per second squared? So, the key to part A is in this last section right here. The boxes move together. The boxes move together, right? With the same velocity and the same acceleration. So if I want to figure out what the acceleration of the whole two box system is, right? Well, how can I figure that out? I have a force, right? I have some masses, and I need to figure out some accelerations, or an acceleration, right? So what kind of equation do you guys think we're going to set up here? F net, yes sir. So F net, that's F net x, right, is equal to mass times acceleration, right? Now, question. We have this force right here, right? We know that's 250 newtons. That's fine. No worries. We need to figure out this acceleration. What's the mass? $25. Okay. All right. You guys are smarter than me because my goofy little brain decided to forget that there's two boxes on the exam, and I just went ahead and I did one box and screwed up parts A through F. So there. Excellent. From the begin with, you guys are doing well. Mass is 25 kilograms, right? Because we're adding up both masses of the boxes to get the acceleration of the two box system, right? So this is two box system. This is the key word here. If we're looking at integrating two boxes, we also have to integrate their two masses and their combined acceleration. And so they're moving at the same acceleration, they're moving at the same velocity, right? That A and B system is the mass here. So this would be like mass A and B is equal to 25 kilograms, right? And that's the push force there. So 250 newtons is equal to 25 kilograms times our acceleration, and acceleration is then equal to 10 meters per second squared, right? And so this 250 newtons, right? It's projected onto A, and that same 250 newtons is projected onto B because they're moving together. Like think of these boxes as glued together essentially, right? So sound good for part A? Any questions at all? This two box system idea where you have to make sure that you're adding up the masses, 20 plus 5 kilograms, in order to figure out the acceleration of both boxes. The whole two box system. Sound good? All right, okay. So for part B is where I dread everything. Draw and label a free body diagram for box A, and separately a free body diagram for box B. Actually, I would argue that box B is where I don't have a problem. Box B is like relatively fine for me personally, but box A is just, I hate box A. I hate box A. So I'll do box B first. I'll get that over with. So I have box B, little center here, right? What forces do I have acting on box B? So we have gravity and normal, right? There's gravity, there's normal, and those should be relatively proportional to each other, right? Because there's no movement across or along the y-axis, right? This thing isn't moving up or down. They're just moving along the horizontal axis there. So they should be relatively the same magnitude there. And then what other forces? We don't have friction, but what other force is acting on B here? So we don't have friction, right? So we can't say kinetic friction because we don't have friction at all. And so we have the force exerted from A to B, right? So I have force of box A on B, right? So the thing is, Eric, this is where you and me both kind of mess things up a bit. Because yes, there is A to B and there's also B to A, right? You're absolutely right. We're not wrong there. The issue is, where do I indicate those forces? So the way I like to think about this, and I understood this after the fact, is I look at what each box is feeling, right? What is this box feeling alone? It's feeling gravity. It's feeling normal force. This is from the earth. This is from the floor, right? And then it's feeling A on B. That's what it's feeling, not what it's exerting. It's only what it's feeling, right? So whenever we think about free body diagrams, we're thinking about what an object is feeling, right? At least with regards or with respect to these problems, right? So for box B, we actually only indicate the force A to B. So for box B, we only indicate what force it is feeling. It's feeling a force of A on itself, B. Now, it wouldn't like necessarily be that push force, right? Because that push force is acting directly on A, specifically on A, but we'll figure out here that this force is actually different, or not this force, my bad, sorry. This force A on B is going to be different than the F push force, because this is speaking about the whole system, right? This is going to be a little bit different, the A on B. Superscript of the object's free body diagram always has the arrow pointing at the title of the object. What do you mean? For the one that superscript is pointing at B, A to B. I mean, yes, I mean, you have the push force acting directly on box A, and that acts on the whole system together. But for this force, we're only like looking at like, it's not normal. I mean, like, okay, so I'm trying to figure out a better way to kind of explain this. So force A on B is like, okay, if I were standing in a line, right? If I was standing in a line, and then someone pushes me with that 250 newtons, and I'm standing in front of this person, right? Well, I'm not going to necessarily be like feeling the full 250 newtons, because this guy pushed 250 newtons on this guy right here, right? But then this guy pushes on me with a different force, and that different force is A to B, right? This 250 newtons is like if we were glued together and we're pushing, because technically these objects are glued together, but we're looking at this A to B is what the B would feel from A. So it's like, if I'm standing in a line, someone pushes me, right, and I fall into the person in front of me, it's what that person in front of me feels, part of that 250 newtons. Does that make sense? Because what this is going to be factoring in, because we're separating box B and box A, right? This force, if I were to think about calculating it, right, if I want FA on B, which is what we'll be doing in part C, and this is MA, right? If I'm only looking at box B, what's my mass here? If I'm looking just at box B, what's my mass? 5, right? So the way I think about it is that this force, or whenever I separate out my free body diagrams, I'm looking only at the perspective of that specific box or that specific object, right? What that object is feeling. So if I want to separate this out and I look at the force that A exerts on B, I feel this force. I'm box B. I feel this force A on B, right? And if I want to calculate that force out, it's not going to be that 250 newtons that the third guy behind us pushed me with, or pushed the other guy behind me with, right? So if we were to, okay, let me just draw it like this. If I have this person, and this person, 1, 2, 3. This person pushed on the second person, 250 newtons, right? And this guy bumped into me with a different force that we're going to be calculating, right? So he felt the full brunt of the 250 newtons. I'm just getting whatever I feel out of that 250 newtons, which is going to be different, right? Because it's like he pushes with the full force of 250. I feel a little bit less than that, essentially. So I feel something else from my perspective. So when you're individualizing the perspectives, when you're looking at one specific object and you're separating it from the overall two-box system, right? You're going to be looking at what this object feels. And what that object feels when we're calculating its perspective, quote unquote, we're going to be factoring in its only mass, right? So that's 5 kilograms times some acceleration. And the acceleration it feels should be the acceleration that the two-box system was pushed with. So when I'm looking at A to B, I want to figure out what force I feel from A, right? My perspective based on my mass, my characteristics. Does that make sense? And Eric, earlier we were talking about the force exerted from A to B and vice versa. Does it make sense why we're only putting in A to B and not B to A this way? Yes, no? I mean, hopefully it does, because I'm just looking at the perspective, right? So I'm just looking at the perspective of box B. What does box B feel? It's only feeling a force from A onto itself. I'm not going to be factoring in what force I exert outwards on another object. So when I'm writing these forces, I just want to look at what forces are acting on me. And so that's why for box A, for example, we have normal force from the floor on the box. We have gravity from the earth on the box. We have that F push force from the hand on box A. And then we have, it's going to be a little bit smaller, right? We have force of B on A. So box A feels a normal force from the floor, a gravity from the earth, a push force from the hand, and then feels also box B kind of pushing against it. So if we were to go back to this example, right? So if this, let's say this is the hand, this is box A, and this is box B, right? So this hand pushes on A with 250 newtons. It feels that F push force alongside these other forces here in the Y direction, right? And it bumps into box B. It'll feel that kind of like obstruction by box B, right? So if you were to like, someone pushes you in gym class or something, right? And you go head first into the wall. Don't tell me you're not going to feel that wall. You're going to feel that wall, right? So it's that force that B acts on with A, right? That's what these are all the forces that I feel from box A. Now, if I look at box B, like let's say that this is the wall or something, right? What does the wall feel? Well, it feels your face or your body hitting that wall, right? It feels A on B, and that's it. We're not factoring in what the wall exerts back on you. So when we separate out our free body diagrams like we do in these types of problems where we have box A and box B, this is why I said these are a nightmare. When you separate them out, you have to indicate the forces that pertain to each box. What does each box feel? So question yourself, what does each box feel, right? Not what forces does it exert. What forces does it feel, not what forces it exerts. So I feel a normal force, I feel gravity, I feel a push force, and I feel that box B acting back on me. If I'm asking for box B, I feel that normal force, I feel that gravity, right? I also feel the box A pushing on me. I don't care when I'm drawing a free body diagram just for box B. If I'm looking just at box B, I don't care at all what force I'm going to be acting back on the other object. I just want to figure out what I feel. So it's a selfish, individualistic kind of perspective on each component. Friction, they said it's frictionless, so we don't have to factor that in. But does that make sense in terms of separating things out? The concept of separating the two perspectives. Okay, I see only one yes, so I mean, that's kind of worrying. What would be the forces that are related by Newton's law? So excellent question. The forces that would be related by Newton's third law would be F, B on A, and F, A on B. Because these are technically an action-reaction pair, right? Because box A feels, like if I were used to that wall example, right? If I use that wall example, so I get pushed into the wall, I feel that wall, but also the wall feels it feels me, basically, right? It feels me bumping into it. If we were to use that wall in gym class kind of example. So A feels that contact with B, and B feels that push from A, right? The rest of these in the Y direction here, are not related in terms of Newton's third law because there's no action-reaction pair. And then F push, right? That's going to be acting on A, but B doesn't necessarily feel the full brunt of the 250 newtons. It's kind of like asking, okay, so like if we were to go back to that example of someone pushing the other person, right? So person 1 pushed person 2 with 250 newtons, and they bump into me with 250 newtons. Am I going to look at the guy number 1? No, I'm most likely going to look at the guy behind me like, hey, what the heck, you bumped into me, right? I don't even think about looking, like my first instinct is like, okay, let me look at the person directly behind me. I don't care about the person who might have instigated or directed the action from the begin with. Like I don't even know that they were there. I didn't know that they were acting that force, right? I'm just looking at the person that I directly felt pushing into me. So when I look at the F push is attributed to, or it applies to, that first object. It applies to part A, or to box A. Box B doesn't feel that full brunt of the 250 newtons when on an individual level. It just feels that box A bumped into it. Box B doesn't have any knowledge of the hand. So box B doesn't know that there's a hand there. Box B only knows that there's A behind it and A bumped into it. But box A knows that there was a hand behind it that pushed it, and then there's a person or a box B in front of it that the box A is gonna feel when it falls over, basically, or when it bumps into box B. Does that make sense? Okay, I hope so, because it's like dead silent in here. Okay, cool. I certainly hope those two like um analogies kind of helped clear things up. I this is this is why I said I hate this. Like, even explaining it to myself, I just sometimes it just sounds weird. So please let me know if you don't understand this, because I promise you, like, I don't want to promise and then like turn out to be a liar, but like I will bet my first future salary on a problem like this popping up on your exam or a quiz. There. I'm betting, I don't know how much that's going to be, but oh, well, sure. Firstborn child. We'll bet that on this problem appearing on the exam or quiz. There. All right. You can catch me in what? 15 years, maybe? Something like that? We'll see. You'd rather take the check over the kid. All right, fair enough. All right. So hopefully that makes sense for part B. Part C, it says, what is the magnitude of the force that box A exerts on box B? So box A on box B is this force right here. Force A on B, right? Mass times acceleration. So the mass of the box B is 5 kilograms, right? But what acceleration does it feel? It feels at 10 meters per second squared, right? So this should give you 50 newtons. And so now you can see why I'm saying, like, it doesn't feel the full brunt of the 250 newtons. It just feels, it has no knowledge of the hand. It just has a knowledge of the person behind him, or the person behind it, right? The box behind it. So box B has no knowledge that there's a hand here pushing 250 newtons. It just knows that box A bumped into it. And so that's why it's different, right? It's, and from an individual perspective, force A on B factors in the mass of B and the acceleration that the whole system feels. Yep, mass of B is 5 kilograms. Yeah, it says apply Newton's second law to just box B. And this should be relatively the same for for your de novo section. For part B, they just wanted you to draw the free body diagram for box B and not box A. And then C is the same as well. Okay. Any other questions about problem 3 at all? Please, like, be 100% honest and upfront if you don't understand something, and I'd be happy to send you an email with a better explanation that's written out and is like done in a more calm context, because sometimes I get nervous during these sessions. So like when I'm calm and I have some air conditioning on and a nice cup of coffee, I'll like, everything makes sense. Yeah, C is that simple. It's just figuring out the force of A on B, and we just apply Newton's second law to the individual perspective of B. What does B feel from A? It feels that, okay, it weighs 5 kilograms and it felt that acceleration of 10 meters per second squared from that overall push. Yeah, this will be posted and uploaded on Google Drive and YouTube. Okay, sounds good. I guess if there aren't any other questions about problem 3, We move on to problem 4. But yeah. All right, now here's the easy stuff, right? Here's the one box scenario that I like. Screw the 2 boxes. This is what I like here. Some good old fashioned trig and 1 box problems, and not any of that BS with box A and box B. So, problem 4, block and a slope. Says we have a block of mass 8 kilograms slides down a slope which is inclined at an angle of 40 degrees. So we have 40-degree angle here. Mass of 8 kilograms. Choose your coordinate system such that the x-axis is oriented along the direction of the acceleration. So, from the beginning, we have this incline, right? So what kind of coordinates do we have? We have normal y and x, or do we have something different? Yep, excellent. Tilted coordinates, absolutely right. So, and here's the thing, right? If you don't, like, it really kind of depends usually on your TA, but whoever's grading your homework, which you almost never know. But, like, just please always write this little bit down. When you have this little picture here that it shows an incline, right? A box sliding down an incline or moving up an incline or whatever, please, please, please draw this little bit right here. Draw a tilted coordinate. And literally just put tilted coordinates. Like, that's literally all you have to do. If you put this little like drawing and the words tilted coordinates there, it helps the TA know that you're thinking about this problem in terms of tilted coordinates, and it's contributing to your points. If they don't see this, at least this was in my year, if they don't see this, it's a solid point off for no good reason. Even though, like, you know and they know that we're solving this problem with tilted coordinates because there's like no way for you to get it right if you're doing it with regular coordinates. So even if you get the right answer, if you don't have this, at least this is in my experience, if you don't have this little bit right here, you're going to get points off. I mean, if you want to risk it, go ahead and don't do it, but I'm telling you from like personal experience, I have lost points for not doing this. So please don't forget this little bit here. Tilted coordinates, put it in, and you're good. Now, we want to draw a free body diagram for the block, right? So I have this block here. And what forces do we have acting on the block? So we have gravity, right? So that's pointing directly downwards. What else? We have normal, right? And we have friction. So normal, what direction would normal be pointing in based on these tilted coordinates? So I know that gravity is pointing downwards like this. Normal would be pointed what? Excellent. Go ahead, sorry, I cut you off. Like this? Yep, exactly. So if we were to kind of describe it, right, based on these tilted coordinates, you're absolutely right. It would be perpendicular to the surface of contact, right? So it'd make a right angle with the surface, which is this incline here. And at the same time, we can actually technically say that this is along the tilted y-axis. So if they were to ask you the direction of normal force, you would say it's pointing along the tilted y-axis. So do this. This is normal force, right? It's along the tilted y-axis, because if we define the y-axis and x-axis to be like this is normal force along the tilted y-axis, So there's our normal force. Our friction is pointing in what direction? So negative x, right? And that's the negative tilted x-axis, so it should be pointing up and to the left on that incline, basically. So it should be like that. Sort of. That's Fk prime. This is kinetic friction because it's sliding, right? It's an object sliding on the surface, so it should be kinetic friction. Fn should be as big as Fg, so that's a good question. The thing is, when we're looking at this, since we have tilted y coordinates, right? It's not Fn that should be big as Fg, but since, okay, so because this is directly like downwards here, right? And that's based on our tilted coordinates. If it's like this, well, that's not in the y direction. It's a little bit of both, right? It's a little bit of y and a little bit of x, right? So that's why we have, and I was going to get to this later, but we have fgx and fgy, right? So technically, your fn should be equal to what? fgy, right? So we want to make sure that these two are proportional in length as well, to indicate that there's no movement across or along the tilted y-axis, right? So this is our this is our y-axis here, right? This is our y-axis. Downwards like this, along the negative tilted y-axis basically, would be the fgy, and we have to cancel that with fn because we don't want any motion in the y-axis, tilted y-axis direction, right? Because there's no net force in that direction, because this block isn't just all of a sudden levitating or sinking through the incline, right? So fn should be equal to fgy, right? And so we have fgx, we have fk prime, we have fg, we have fn, and I believe that is it for our free body diagram. So fgx, fgy, fn, fk prime. Sound good so far? Yeah, you have to draw fgy and fgx whenever you're doing tilted coordinates, because they're more likely than not to ask you about either calculating them out directly or figuring out some kind of like, or they might give you them, for example, or you calculate them and use them to figure out normal force, for example, or something like that. And one more thing that we can add is that this angle right here, so if we were to draw this, right, this is the angle of incline, this is 40 degrees. So this was your fgy, this is your fgx. The angle right here is equal to this angle right here. So the angle of incline is equal to the angle that you have right here in this little like makeshift triangle that you do when you're describing your fgx and fgy forces. Sound good? Any questions? Okay, so yeah, we can just label this as 40 degrees as well. Now we got to figure out magnitude of normal force on the block. So we want to figure out normal force. This is along the tilted y-axis, right? The other force that would be acting the y-axis would be fgy, right? So if we want to figure this out, well, we would also have to figure out fgy because we don't know that. How can we figure out fgy? Trig, right? Because we have Fg, we can figure that out because we have the mass. Fg is equal to mg, that's 8 kilograms times 10 meters per second squared. And that's 80 newtons there for Fg. So we can calculate Fgy using trig, right? So Fgy, how can we figure that out? Which trig function can we use to figure out Fgy? So we have Fg, this is technically our hypotenuse, right? We want to figure out Fgy, and we have this angle 40 degrees. Cosine 40, yep, so we have Fgy over Fg, that's equal to cosine 40, right? Because here's the angle here, adjacent over hypotenuse, right? Adjacent to the angle next to the angle over the hypotenuse, right? The longest side on a triangle. So Fgy over Fg is equal to cosine 40. We have Fg, that's 80 newtons, so 80 cosine 40 should give us Fgy, right? And then that gives us our Fgy. Once again, I don't have my freaking calculator. So please someone let me know what you got for 80 cosine 40 there. I think it should be around like maybe, no, never mind. 61.28. Let me try and, okay, what's cosine 40? Let me just look that up real quick. Cosine 40, and okay, there's no reason for, that's okay, it's 0.76, and that's times 80. Yeah, I got 61.28, 61.3 about. So, I personally recommend at least carrying 2 decimal places. So I would do 61.28 because I just don't like to round too early into the problem, because especially if you're doing the online homework, if you round a lot, that'll throw things off. So yeah, 61.28 is what I would put for FGY. And then we can set up an FNet, right? FNet Y. We know that that has to be 0 because there's no movement in the Y direction based on the context of the problem. And we know that this Fn is pointing in the tilted Y direction, FGY in the negative tilted Y direction as well. So Fn minus FGY is equal to 0, right? And so Fn is equal to FGY. Fn minus 61.28 newtons gives us Fn is 61.28 newtons, right? Now, if I were to ask, what is the force of gravity in the y direction, right? What's FGY alone, right? Without the magnitude, I would have to say this is negative 61.28 newtons for FGY, because it's pointing along the negative tilted y-axis, right? But since we're throwing in the negative sign from the beginning in the equation, we just throw in the magnitude, right? We just throw in the 61.28. So we do Fn minus 61.28, and we set it equal to 0. Add things over, and you get normal force is equal to 61.28 newtons. That's our magnitude for the normal force. Like I said before, if you want to do Fn plus FGY, you would have to throw in a negative 61.28. Hold up. Something wrong with my pencil here. Oh, wow. It just stopped writing altogether. That is not good. Okay, hold up. Oh, that's poor. Hold up. Okay. I'm gonna okay. Thank God. I thought I was about to have to drop another $100 or something on this freaking device. All right. So that's 61.28 newtons for our normal force. Makes sense for part B? Any questions at all? Makes sense? Okay, cool. Now, part C, coefficient of friction between the block and the slope is 0.6. So that's mu is equal to 0.6, right? That's our coefficient of friction. And that's unitless. What is the magnitude of the block's acceleration as it moves down the slope? So we have this mu is equal to 0.6. We have fk prime. We know that fk prime is equal to mu times Fn, right? And we want to figure out what the block's acceleration is as it moves down the slope, right? So when we're looking at moving down the slope, what does that mean? What direction are we moving? If we're moving down the slope. So negative how? Because you would be moving down the slope here, right? So remember, this is tilted coordinates. So you'd be technically moving along the positive x-axis, right? Because if this is tilted y and tilted x, and the slope is sliding down, or the box is sliding down this way, it'd be along the positive tilted x-axis, right? Yep. And so in that case, if we're trying to figure out, well, we can figure out friction, right? We can figure out friction because we have the normal force from earlier, and we have the coefficient of friction, right? So we can have access to fk prime. That's in the x-axis, tilted x-axis direction, right? If we're trying to figure out the acceleration as it moves down the slope, right? acceleration down the slope, well, we also have our forces on the x-axis, so what can we do to figure out the acceleration down the slope? If I want to figure out acceleration x, basically, how can I figure out acceleration x? Or, yeah. What can I do? Can I set up an equation? Can I don't know, do something else? What do I got to do here? So we have, okay, so Matthew said Fn times u, so that'll give you your kinetic friction there, and that's equal to max, okay, sine theta. So why would you multiply by sine theta? If you don't mind explaining. I'm just a little curious there because the fk prime, right? Like I get that because you would multiply Fn times u. That's a component of the x-axis. Okay, that's an interesting way to do it. I would also ask you what other forces are acting in the x direction, because is kinetic friction acting alone there? Because kinetic friction would just be the force that's opposing the motion, right? And we want to figure out the acceleration of the box. So if that box is moving along the x-axis, there's kinetic friction, but there's also what? FGX is also acting on it, right? So you're right in the fact that we have to set up some kind of net force, F net x equation, right? So net force equation, the x-axis, right? So that's max. And then that would be equal to your FGX minus your FK prime, right? So we have to think about FGX along the positive tilted x-axis, subtract that FK prime along the negative x-axis, and that gives us our max, right? Our net force, mass times acceleration for the x direction, right? And we have the mass of the box, so we can just figure out the acceleration in the x direction because we can figure out FGX as well using trig, and we have FK prime, we can figure that out using the values given in the problem here. But that little part about the sine theta, I'm just kind of curious as to why you would put sine theta there. I'm trying to think of it. Because I mean, like, FGX, in order to get it, yes, we'd have to do sine. So I'm guessing maybe that's kind of how you thought of it. But you're on, like, either I'm missing something, like, mathematically, and you're absolutely right, or, and you kind of, like, I guess, did the math quicker than I did, or I'm, like, I don't know, or you're missing something, I don't know. But, like, you're on the right track, I'm pretty sure. It just, I think you were missing the FK prime, the kinetic friction component. Does that sound good so far, Matthew? Or are you still kind of confused, or what's going on? So the cosine, sine, or tangent stuff, that's going to be factored in when we're trying to figure out a specific force, right? So just looking at this net force equation, right, I want to factor in what forces are acting along the x-axis. So I see that there's an FGX component and then there's an FK prime component along that tilted x-axis, right? So if I'm setting up my F net equation, I have to set it up in a way that incorporates all the forces acting in the x direction. So there's FGX in the positive tilted x-axis minus FK prime, which points in the negative tilted x-axis, right? That's my F net equation. In order to figure out what FGX is, I can then use my trigonometric functions to figure out what FGX is. So I can do that by doing, okay, well, FGX, we have this angle here that's opposite to the angle, and we have this hypotenuse, right, which is FG. So if I do like sine 40 is equal to FGX divided by FG, that's opposite over hypotenuse, right? Opposite over hypotenuse. Sine 40 is equal to opposite over hypotenuse. And that's when you would use your trig functions to figure out unknown forces. But I don't think you ever use your trig functions or throw in like a sine or a cosine when you're calculating like the acceleration here. Because usually to avoid like throwing in sine and cosine and whatnot and your F net equations and stuff, that's why we separate things out into F net X and F net Y. We look at things separately, and then if we need to figure out a force along some kind of tilted axis or something, we can use trig to figure out that force and what it would be relative to a tilted adjusted axis, right? This is for Professor Yordanova's version. F net U calculated. Yeah, so I forgot about Yordanova's section. For part B on Yordanova's section, they were just asking you to figure out the mass of the block because they didn't give you the mass. They just gave you the normal force. And then, so you said F net you calculated is negative. I'm not sure if you did something wrong. F net is negative. Does that mean the block is accelerating in negative x direction? So the acceleration I believe that we're going to get is going to be negative, I think. Or at least that's the acceleration that I got for part C on Yordanova's written homework. And so if you're moving along that x-axis, right, that positive x-axis, well, your velocity is positive, right? Because you're moving along the positive x-axis. So your velocity is positive. If your acceleration is negative, right, then that box is essentially slowing down, right? Acceleration is pointing in the opposite direction. So your F net is negative. The block is, there's a net force in the negative x direction, yes. So there's a negative acceleration, therefore negative force, or negative net force in the x direction, which just means that the block is eventually, coming to a slow stop, right? So it's still moving in that positive x direction, it's just slowing down, basically. So yeah, remember that your velocity and acceleration, for you to be slowing down, they have to be opposite signs. For you to be speeding up, they have to be the same signs. And so if there was a positive net force, right, your acceleration is the same direction as the velocity. They're both positive, and so there would be a net force in the positive tilted x direction. But since we get a negative acceleration on Yordanova's problem, which, like I said, I'll upload that stuff, negative acceleration would indicate that there's a negative net force. So that would mean that Fk prime overwhelms Fgx. It's bigger than Fgx. And so there's a net negative force. That friction is going to be larger, and that's going to slow it down to a stop, basically, eventually. But Matthew, does that make sense on when to use cosine, sine, tangent stuff? You only use it when you're trying to figure out like components of forces. And then you throw those components, like you throw in Fgx or Fgy into your F net equation. I don't think we ever put in like sine or cosine directly into the net force equation, unless like if you want to throw in all the work there, sure. But I usually just figure things out separately. If I have to figure out this part right here, I do that separately, and then I throw it into the equation. Otherwise, like if you did for FGY, right? FGY is equal to 80 cosine 40. You could say like Fn minus 80 cosine 40. And then that regardless, that still gives you FGY. It's just that you figure out the component separately, and then you throw it into the equation. Does that make sense? You sure you got it? I just want to make sure, like, I'll try and repeat it a different way, but I just want to make sure that we're moving on and we're all on the same page. Otherwise, like, once we finish, like, I'd be happy to explain it again. But yeah. Yeah, you use the sine, cosine, tangent stuff when you're finding components of a force, x and y components, and if there's especially like it's tilted like this, right? So if I want to use sine, cosine, tangent, I'd use that to figure out like FGX and FGY, and then once I figure out FGX or FGY, I can throw those into an F net x or an F net y equation to find out other components in the y or an x direction. Sound good? Okay, cool. So we have F net x equals MAX equals FGX minus FK prime. So we have FK prime here. That's equal to 0.6, the coefficient of friction, times the normal force. The normal force was 61.28 newtons. Right? So FK prime is what? What did you guys get for FK prime? Any takers? 36.77. Yep, that's about what I got. 36.77 newtons, right? For FK prime. So that's FGX minus, well, I'll actually calculate FGX first too. So how can we get FGX? We can do trig again, right? If we want to figure out what FGX is, we can do trig. We know that FG is equal to 80 newtons, right? FG is equal to 80 newtons. So what trigonometric function can we use to figure out FGX? We're using sine, cosine, tangent. What's going on? Sine, right? So sine of 40 degrees. So sine is opposite over hypotenuse. So FGX over FG, right? And FG is 80. So if this is 80 right here, 80 newtons. So 80 newtons times sine 40 will give us FGX, right? So let me write it down here again. FGX over FG is equal to sine 40. This is equal to FGX over 80 newtons. So FGX is equal to 80 times sine 40, right? So what do you guys get for 80 sine 40? Yep, 51.42 newtons, right? So then we can just throw that back into equation, 51.42 newtons, minus, move things over here. Oops. Okay, that's horrible. There we go. Move it over there. 51.42 newtons minus FK prime, that's 36.77 newtons. And that's equal to MAX. The mass was 8 kilograms. So 8 kilograms times AX, and then we can just solve for AX, right? So we just take 51.42 minus 36.77, right? And then divide that by 8 kilograms, and that should give us around, I got 1.83 meters per second squared, I believe, if I did my math correctly. Anyone want to check that? Yep. Okay, awesome. So that's A, B, and C of problem 4. Any questions about problem 4? Any of the other problems here? Let me take a look at Yordanova's section 2 to make sure that... Okay, yeah. So for part C on Yordanova's section for problem 4, they had the coefficient of friction as 1.2, and you still needed to figure out the acceleration. So actually, yeah, my bad. Then the acceleration that you get here is actually positive. So, and the other one, you have it as negative. So there's that. At least I hope I did everything here right. Let me see if I do. Let me calculate something out here real quick. Yeah, if some of you guys have to head out, go ahead. I just want to make sure that this part was done correctly and I didn't mess up part B either. But yeah, no problem. And I don't know, for those who wanted to ask questions after, I mean, I don't have much time, but I can probably take a look and I'll send you like an email or something later with whatever questions you guys have trouble with. But I believe that's everything for problem 4. I just hope I didn't mess anything up. I would just Fn minus FGY. Okay, we did that. And then, yeah, for sure. No problem, guys. I guess, okay, if y'all all just want to leave, that's okay. No worries. All right, I will now just probably end the recording. And that'll be the end of it. I'll check that everything is okay, and if I see anything wrong, I'll let you guys know and upload any corrections. But yeah, that's it.